so I want to invite everybody into the meeting and thank you for being here. I am going to take this first 10 minutes or so to start. My speech is going to be broken up because while I'm doing this, I'm admitting people and kicking out note takers. So, first off, today's forum is to discuss in more detail a topic that we presented a while back. I think it was a month or so or more ago. And this is about photonic computing and photonic processing. The idea behind it, and Robert will go into this in more detail, is why are we using digital when we and trying to get to quantum when we could accomplish the same or similar with photons and with light waves. So Robert will start off with his, talking about his patents and his ideas and what brought him to this point. Then I want to talk to the people that are here, and I'm hoping there's a lot of people here that are playing in this field and in these sciences.
That's fine.
And Patrick, if you could mute, please. I'll mute Patrick. But yeah, the people that are here that are in these sciences, in these fields, I want to talk about what is the current state of the art. Where are we in this process? What products are out there? What research is being done, and get an idea of that. And then I want to get into the art of the possible. And that is what are the next steps to get there? I mean, this is all great ideas, but great ideas aren't something that you can implement. You need a solution. You need a combination of solutions to be able to come up with an implementation of a service or of a product. So that is where we're going to talk about the possibility of setting up a consortia. If there are people within a specific industry, in Department of Defense that would like to try and advance this, we can do that. We're doing something similar with Fusion for National Defense, or part of a group for that consortium. So that is the goal here. And for those of you that are new, what we do here at Technology Ideation on these forums is basically brainstorming. We want to bring in solutions and bring in people from many different sciences, many different industries to take a look at these solutions, because the solution may be designed for one particular industry, but it may apply to others. And by bringing in that diversity, we can identify where else those cross-industry, cross-science applications for these solutions. We can also identify who has the pain that this solution can solve. There's a lot of people out there that help small businesses with SBIR funding and and grants and STTR funds and stuff like that. There are people out there that present challenges. This is our niche. We start from the solution side of it, and then we set up as many potential relationships as possible, and then we work to advance those even further. So I'm going to ask, is there any questions for me before we move on from the audience? Okay, Brett, I'm going to mute you. All right, so I'm not hearing anything from anybody. So at this point, I'm going to turn it over to Robert Lyden. He is the regular guy that came up with these wonderful ideas. So Robert, go ahead.
All right. Well, I'm Robert, and I don't know what the background of everybody in the audience is, so I'm going to put this. I'm going to start. I guess imagining that nobody knows anything about what kind of computer they're using in the digital system, and I'll just explain very simply something about the digital system and what the inherent bottleneck is with the digital system. So the computers that you're all on right now, they use transistors, and transistors are glorified on and off switches, kind of like the toggle switches you have on your wall for turning lights on and off. And this is to simplify things, but the switch is either on or off. It's a 1 or a 0. And so using transistors in computers, you're able to store data in digital binary form, as ones and zeros. And so you can manipulate it that way in your processors. You can store it that way in memory devices. And that's basically what you've all got on your desk. The problem with the digital system, at least one of them, is this. If you want to represent and say a letter of the alphabet like A, you've got to send 8 ones and zeros to say A. And they have to be sent in a sequence. So you have I forget what it is for A, but it'll be a 0 and a 1 and a 0 and a 1 and a 1 and a 0, 8 of them in a row. And it takes about a picosecond, give or take, what kind of computer you've got, how fast it is, a lot of things, your operating system. It takes about a picosecond to send each one of those ones and zeros in a series, one after another. And so to say A, you got to say 1 0 1 0, and they all take that long. So you're looking at, 8 picoseconds to say one thing. And the way it communicates that is with ones and zeros and using square waves. Square wave is just what it sounds like. It looks like this. And a tall one is a 1, and a short one or non-existent one in some cases can be a 0. So you've got to create all these square waves to say all these ones and zeros. And to do that, you've got to be switching on and off constantly. And the switching circuits usually have, several electronic components in them, like 2 capacitors at least. And they have to be charged and discharged. And you're all doing this over wires. So you've got wires which have electrical resistance with electronic components doing all the switching to switch on and off to create all these square waves. And then you've got to do it in a sequence. And that is the reason why it burns up a lot of energy. You've got resistance in wires. You've got a lot of switching go on with electronic components, and it's happening very fast. But when you're trying to send a lot of data or do a lot of computations, a lot of energy is getting burned up because of that. So that's one inherent bottleneck in the digital system. It's just the way it is. Can't really get away from that too easily. Not using electronic classical computers, which is what you got on your desk. The next bottleneck in the digital system, using the digital system, is that when you're working on a computer, for example, here, or if you've got a data center, and you want to send information somewhere through fiber optic cable across the country, it's happening right now. All of you got digital computers that are converting stuff, gets converted to, at some point, not maybe on your desk, but gets converted to analog. It gets sent as frequencies of infrared light, and then it arrives where it's going to go to, and it has to be converted back from analog to digital. So there's this constant digital to analog to digital conversion going on. Takes time, burns up a lot of energy. So that's the second big bottleneck with using the digital system. And
so Robert, this is Eugene. I'm sorry, I want to interrupt you for a second here. I just wanted to highlight to the attendees, if you have a question or a comment, please, I mean, don't wait until Robert stops, raise your hand. We want to address any questions that people may have when they're thinking about them, rather than at the end of this. So this is supposed to be live and interactive, so feel free to interrupt and chime in.
Okay, so I'm about done with the kind of the introduction. So the thing to realize is this is what's going on. This is what you're dealing with the digital system. And what they're trying to do now, one of the big problems with the digital system is you can't really process things in parallel. So it's always a sequence. It's this slow stream. And this whole bit about quantum computing is about creating, call them qubits, you know. What they're doing is they're creating a superposition relationship between two things, and that was then called entanglement. And they're using that to try to make the digital system operate in a way that they can do parallel processing. And when you boil down all the catchwords and what's really going on, that's what they're trying to do. They're trying to do parallel processing using the digital system, using ones and zeros. And the way they're going about it requires a lot of energy and isn't the best. And the truth is, and this is, you know, the punchline here, when you use light, when you have a source of light, and there's a plurality of beams of light generated from that source of light at the same time, whether it goes through a prism or a diffraction grating, you already have superposition going on. They're already related to one another, and you already have some degree of entanglement. And what I have done, what I recognized was that, gee, this digital system's really cumbersome. Saying 8 things to say one thing, and then you got to say it in little pieces, kind of silly. So what I did, and what I got in patent claims and such, is I said, look, we can directly encode a specific wavelength and frequency of light, whether it's infrared spectrum or visible spectrum or somewhere in between. We can directly encode specific wavelengths and frequencies of light to mean the letter A, and a different one to say B, and a different one to say the letter C. So you can directly encode different colors, if you will, of light to indicate different letters of the alphabet, numbers, symbols, and that's what I did, and that's what I have patent claims for, that and other things. So it's directly encoding. It's saying, hey, I don't need 8 ones and zeros, the digital thing in a slow stream. I can basically send and detect this color, and it means this, and it's instant, and it requires little or no energy to do that because optical computing, fiber optics, have almost no resistance. So I'm going to stop right there if there's any questions on that much, and then I'll kind of continue. Any questions on that part? Everybody following that so far? Okay. So the first patent I did, the first claim basically claims directly encoding visible or invisible light to represent and encode letters of the alphabet, words, numbers, symbols. And so I've got that. That first patent also teaches and explains how you can communicate really big numbers really fast. And right
Robert,
now, yep.
I do have a question.
Good.
So, Patrick, go ahead.
Yeah, so I was wondering what's the limit in terms of how many symbols can you encode in wavelength? And obviously, your example was like A, B, C, D,
Sure.
and that's ASCII, and now everything is moved to Unicode, and you have like
Right.
a character set explosion. So I'm just trying to understand the utility in terms of based on discrete wavelengths, basically, how many unique symbols can you encode?
I would say infinite, which would probably shock some people, but let's just say you can do a hell of a lot of them. And to explain that, we'd have to go into like what is light, and light being a quantum object and a lot of other things. But you can use frequencies of light, and and we look at frequencies of light as in nanometers, but that's kind of an arbitrary yardstick. I mean, there's things smaller than nanometers. So basically, if you want to use visible light and infrared light, you're starting at about, let's say, 350 nanometers, and you're going up to about 750 or so in the visible range, or 700. Different people can see different amounts. Cats can see different than people can, and you're getting up towards like 2000 in the infrared range. So right there, you've got a pretty big spectrum of frequencies and wavelengths you can use to encode this. And if you're talking like, well, how many letters of alphabet are there? Well, it's 26. And how many numbers? Well, they're really 0 through 9, and then they repeat in some organized way, and we'll get to that. And then you get some symbols. If you had 20 symbols or so, you could probably do, if you have those three things, you can probably do 99% of most of the manipulation you need to do. And so you don't need a lot of different specifically assigned wavelengths to do that. I mean, if you got 10, you can do numbers. So I don't know if that answers.
I think it does.
Yeah, well, there's some deeper stuff we could go into, but basically, you can send more data, and there's ways, I taught in the patent, where you can use multiple wavelengths to basically create encoding schemes like DNA. DNA has 4 different, pieces that are put together. If you can imagine those 4 pieces in DNA being 4 different colors,
sure,
and using combinations of those 4 different colors in a series, you're basically optically then creating DNA.
Yeah, you're overcoming the limitations of binary, which is kind of cool.
Yeah, and somebody said, and I don't know if it's true, I remember reading, somebody said you could take all the data in the world, and if you recorded it as DNA, it would fit in something the size of a golf ball. So if, depending on how you do it, you can manipulate light to do DNA-ish sort of things, and store information. So
you're leveling up from a base 2 language to like a base N language, where N is actually a relatively large number in the way you encode it. It feels like the practical implementation of something like this is with existing fiber optic infrastructure to have an encoder and decoder on each end. So is that what you're engineering towards?
No, that's actually not the, at this point, it's funny. When I first filed this patent, I realized I was ahead of the wave, and you don't know if the wave's going to come in 5 years or 10 years or 20 years sometimes, or if you're just flat out crazy, But it looks like I was maybe 3 to 5 years ahead of the big wave. But now, right now, everybody, literally every day, my feed, probably because it knows what kind of things I look at. There's some new company making some new optical coupler switcher, multi-wave division, multiplier. There's all kinds of things out there right now to send multiple frequencies of light and to receive multiple frequencies of light through fiber optic cable. So the connectivity and the ability to generate light in the light source and the signals, the ability to receive it, it's actually all out there, and somebody just needs to put it all together. to have a working optical computer. There's one area that I feel hasn't been done, and my last patent is directed to that, and I'll get to that in a little bit. But most of the stuff for generating the light, sending the light, being able to detect it and interpret it, that's all there. That part's there, and you can go shopping for it right now. So one of the things I figured out, and I'll talk about how to send big numbers with light. And this
before you go on, I want to add a few things here. That there are in existence optical processors. There are people that are working diligently and starting to make optical processors. I know that one of the things we were doing is putting waveguides inside of chips as a way to try and stop that conversion from inside the chip or the losses from inside the chip to copper, and with RF.
Yeah, there's optical logic chips being made. There's not a lot of companies making them, but I'd say there's probably at least half a dozen to a dozen out there fooling around in this area, and some are doing better work, and some have things I think you can buy off the shelf. I think one of the people I'm impressed with is a man named Michael. He's got a company. He's a CEO of a company over in Europe called Qant. It's called Q.ANT, like ant. And I'm not going to murder his last name, but it starts with an F because I'm not sure the German pronunciation. But he's got basically a working. You can buy it. You can install it with digital, hardware, and it'll do optical processing. It's so there's optical neural network things out there. Xanadu has something like that too, and there's some optical chips being made. But I would say, and there's a few companies that are trying to make optical computers now, and putting some of those components together. So the chips are there, or darn near close, I'd say. And where I feel the issue is, or the bottleneck really with an optical computer right now, the piece of equipment you really need is the memory, and the memory processing being hybrid, all put together. And that's what I teach and show in my last patent, and I'll get to that in a little bit. But before I get to that one, I'll just explain so people could understand how you can send huge numbers really fast. If you send like a number like 1,000,000 something or other with digital, it's something like 34 bits that you need. And of course, each of those bits are sent one after another, a picosecond apiece. But if you take the digits of a number that's 1,000,000 something or other, and you basically send the base portion, whether it's a 1 or a 2 or a 3, and you send it with a pair with what its placeholder value is, 10 to the 1, 10 to the second or something. If you send the base portion of a large number with another number as a pair that basically has its placeholder value or its exponential value, it requires half the number of things to be sent, and you can send them all at once simultaneously because they sort themselves out on the other end. 10 to the 5th is 10 to the 5th, 10 to the 6th is 10 to the 6th, and so you can send in parallel a very large number in as little as, the period of visible light waves is around 2 femtoseconds. And conceivably, you could analyze even less than that and know what it is. But for sake of bandwidth and accuracy, let's say you repeat it 10 times or 100 times. 100 times 2 femtoseconds is 200 femtoseconds. That's still a lot faster than 1 picosecond, and they've got to send eight of them. So you could send almost an infinitely large number with these related pairs all at once in a few femtoseconds, and it's gone, and it's there. So when you talk about like processing data, a lot of data processing dealing with numbers and computations with numbers, it's a way of making it go wicked fast with very little energy consumption. So there's a claim, I think the first claim in my first patent is for the broad thing, directly encoding alphabetical letters, numbers, symbols, and so on using visible and invisible light. And I think claim 16 talks about this big number thing, how to send big numbers. And then there's a claim 28 where I got broad claims for an optical, electrical, electro-optical, and or quantum computer doing this. So there's actually an issued claim for an optical, electro-optical, or quantum computer where you're sending the data in the form of visible and invisible light that directly encodes the data you're sending. So that's kind of the first one. The second one I basically have added, because we're living in a digital world, the ability to send this information as sine waves or square waves and or together in a relationship. So that's there. And the third one adds wavelets and pulses, because you can actually encode a wavelet and a pulse to do the same kind of thing depending on the frequency that you're sending. And wavelets can contain information having to do with time and some other things that a normal sine wave can't. So that's kind of in the third one, and that gets me to the newest one, and that's the one where I'm trying to deal with, okay, what's missing in this big equation? What would make this go really well?
Before you go on, I want to go ahead and ask if anybody has any questions.
Sure.
Anybody have any questions up to this point? Please just raise your hand or just chime in, unmute and chime in.
Well, they'll probably have questions after the next part. So what I looked at is,
I hope so, because this is supposed to be live and interactive.
Well, it's okay if it's not so interactive. It's all right. My feelings won't be hurt. But so I looked at the whole picture, and it looks to me like we've got ways of generating different wavelengths and frequencies of light, and we can communicate it, and we can receive it and detect it. And we've got people making optical processors and optical neural networks. So we've got some of the processing thing done. And one of the key areas that needs to be better is memory, optical memory. And it's known to store optical information on disks, DVDs, CDs. And it had been done by basically burning, kind of like dots and dashes, ones and zeros into the substrate. And kind of the prior art was, well, you can burn them, or you can read from them, and you can watch your movie, and there were laser discs. And people have done holographic storage of light. And the things that you'll see is they'll have like a square cube, square cube looking thing, and basically they shine a beam of light, and they actually shine two usually to put the information in. There's a data beam and there's a reference beam, and then they can store the information in this holographic storage material, which is usually a crystalline material, glass or crystal. And Microsoft has a program, they were doing that. They're calling it Project Silica, where they're storing things on crystalline material, kind of like the Superman movie, And so that's out there. But when I looked at the big picture, what was missing is if you really want to do AI, and if you want to do a lot of complex analysis, you want to have something like the human brain. And we have photodetectors, and those photodetectors go to our brain. And our brain has specialized parts that deal with vision, hearing, touch, and so on. So you've got this memory thing up here, and the memory thing has specialized sections for processing certain types of information. And those different sections can crosstalk and talk with one another. And then you've also got a logic chip up here. You know, you've got your logic center that does computations, and it does it all at once. So we are like the best electro-optical analog kind of biochemistry thing you can pretty much think of. That's how our brain works. We process simultaneously a lot of things, and we're able to put it all together and do a lot with it. And our brain actually is very efficient at it in terms of how much energy it requires to do that. I mean, if we could do that, we'd be way ahead of the game. We could make a really artificial brain. So what I did is I said, okay, so we don't want to have the data come in to one little thing and store one little bit of data here and then use a reference beam and pull it out, like in, out, one thing. What we'd like to have, and we work with digital a lot, so you know you've got 8 digits with 8-digit format with digital. Why don't we have something that's shaped like an octagon? It has 8 sides or 8 portions to it. And we bring the data stream of light in there, multiple ones, and they can simultaneously write to a bunch of them, you know, where you can store and record data, not just to one, let's say 8 of them or 12 of them, make as many as you want. So the data can come in, a lot of data, and you can store it simultaneously, okay? And you can retrieve it simultaneously from a bunch in parallel. So parallel storage, parallel retrieval. And then take each one of those segments, you know, think about how the brain works. Some of them might be specialized for certain things. Some of them might be specialized for certain types of memory, RAM, ROM, cache, okay? And let's make each one of these parts be able to talk with one another, because that's what your brain does. And then let's have each one of these parts be attached to, connected to a processing chip, a processor, a logic processor, a neural network. So let's say you've got your 8 pieces of memory substrate, and they can pull information in and out simultaneously in parallel. They can talk to one another. They can each talk to their processing units, and those processing units can talk to one another. If you do that, you've got something that's starting to look and act like the human brain. And your processing capability goes up just huge. And you can do it if you're using light, because light is fast and it doesn't require much energy. There's not much energy loss. So what I basically looked at was we need to create a type of memory, optical memory, that can simultaneously store multiple pieces and streams of data. And it can talk to itself back and forth. You know, those various things can be related. They can be processed, all of it happening at the same time in parallel. So that's basically what's in one of the key things that's in the new patent application I filed. Teaching, we need to have, and ideally a hybrid memory and processing device that looks like this. And you know, I think the place to start is to build it on a tabletop, build it big, and then make it small. So that's in there. And one of the other things that's in there is when you look at optical information, there's images, there's photos, there's things like that that some can be directly reproduced and directly recorded. So you're getting beyond words and sentences. You can a whole page of literature, boom, an image. I looked at optical patterns and how you could, for example, turn binary, even if you want, into an optical pattern. Dark and light circles, gives you digital information if you want to do 8 of them, if you want to crosstalk. And when information is sent through optical fiber cables, some of you may know they use constellation patterns, and those constellation patterns are kind of circular. There's four quadrants, and it's a circular kind of thing. And they'll put the ones and the zeros in different positions. And one of the things I suggest is that, you can do that. But we can also directly encode numbers with a particular color, if you will. And whenever you send that color, it means the number 2. But we could also send numbers in a way where the space in which it's in terms of phase shifting, also indicates the number. So you'd have like double redundancy. You're sending a wavelength of color that means 2, but you're also sending it in the 2 spot in a constellation diagram or scheme of things. So that would do a lot to with regard to error detection and that kind of thing. It's a kind of double redundancy that you could do. So I'm going to stop right there, and let's see if there's any questions on that much.
Has there been any work in this? I mean, have people?
Frankly, as far as designing that kind of an optical memory processor, doing all that kind of thing, I don't think so. I mean, if it's being done, it's confidential somewhere.
Yeah.
Yeah, not that I know of. I think the closest that I know of is DVDs, laser discs, your basic holograph storing, what Microsoft has done. I don't think anybody I'm not aware of anybody saying, look, you should actually have this memory have a bunch of sections and portions, and you should be able to simultaneously store information, retrieve information from all of them, and they should also be able to crosstalk, and they should also be linked to multiple logic processors and neural networks and things, so that there can be simultaneous parallel processing going on too. If you do something like that, you've got something that starts to act and has kind of the capabilities that the human brain does. If you're just going into one thing and, well, we're going to write to it and we're going to retrieve from it, you're slow. I mean, you might be faster than everybody right now because, people aren't even doing that much, but what's the next step after that? You're going to want to be able to do as much of this as you can, as efficiently as you can. And I think that sort of architecture structure will do it. And if you're using light and it's directly encoded, it's fast. There's nothing faster, and there isn't anything that takes less energy. So I think, tackling that and making that, if you want to call it a chip, but a optical memory, hybrid memory processing chip that'll do that, is where somebody should be really jumping on and tackling, because I think most of the rest of it is out there or nearly out there on the shelves, and you can put together the rest of it, but the heart of it, the key part to have is to have that hybrid optical memory and processing capability. If you've got that, I mean, right now they're talking about how, quantum computers are so much faster than what we can do now with blah, blah, blah. And the truth is they're only processing, a related pair. If a superposition relationship correlation is being created where if one thing is red, the other one's blue. So when you unpack it at some point, if you get the blue one, well, the other one's red. It's not super magic, but what I'm talking about is you could be doing that with dozens or hundreds of correlated beams of light, not just one, maybe hundreds. How much faster is that? And you're not going to involve all this digital process that takes so damn slow. Because when they do it, they got to send 8 ones and zeros even to correlate the two digital things. So you can do that. And then on the other end, the processing part, well, if you've got a processor that acts like the way I just described, it's not going to be 1,000 times faster. It's going to be probably millions of times faster. And that's where I think things will eventually go. And so that's what I see happening.
Okay, we got a question here.
Sure.
Brian, go ahead.
I have a question. So if someone spends $1 billion on a digital data center this year, okay, I could imagine a photonics data center being built in a couple years that's 100 times smaller, yet 100 times more powerful.
Or more.
And I'm also wondering, I have this idea, if you have a huge data center and you could put a value on its performance, okay?
Mm-hmm.
If you instead built that out of your patents, could you make that data center mobile down to maybe as small as a command truck or a shipping container, and then have a mobile data center?
Well, I think the answer is yes, because if you look at computing power, what they're doing, using the digital method, most of it, they're starting to integrate some optical with what they're trying to do this quantum stuff, which is going to help. But the bottom line is they got this big energy requirement, and then they've got, a lot of them have this big cooling requirement, and it's all just to make it, because we're hanging on to the digital system for dear life because it's all we've known for 50 years, and nobody's really thought outside the box and said, yeah, but you don't really need that, I don't know how many of you got in a car today and drove, but you stop at something called a stoplight, and it's got 3 colors that shine, and you've got these optical detectors, and when you see the green, somewhere your software got loaded when you had driver instruction 101 or something that, green means go, I can go. And so you do that processing and you do it. And so it's kind of funny, light's out there and you can use light to send data. And we do every day when we drive our cars in a way. But the short answer to the long question is, I am frightened, frankly, and bothered by what I see as our multi-billion-dollar blunders that we're doing right now to build data centers based on the digital system. We're going to have it. They should exist, but to have the future built on the digital system and to have these data centers, which are going to consume huge amounts of energy and cost a lot and be big, I think it's the biggest white elephant blunder of a generation. Because the optical computing, electrical optical computing, quantum computing based upon that, because the thing is, the electrical optical computing is already quantum computing, or can be. And so
let me stop you, Robert. We're going down another path here, and we had a couple questions.
Sure.
That I want to get to. So, Alexander, you're first.
Hi, I'm wondering how easy it is to control the light across, distances.
Well, they do it now, with sending binary, and depending on how far you go, they have things to amplify the light, and they have things to focus the beams and so on. I think the equipment already exists to send light and manipulate it and keep the signal strong and true. We just haven't been trying to do it with more than a couple frequencies of it. We've been sending ones and zeros, and we haven't been trying to send 30 or 300 different frequencies and doing the same thing. So exactly. I don't think that's the technical problem. I think, as I said, the biggest technical thing to tackle, I think, is the hybrid optical processor, memory and processor. And I guess going back to finish what I was saying about the big data centers without bashing things too much, but I think we're making multi-billion-dollar blunders by building data centers on a technology that I can see is already obsolete or will soon be, probably before the buildings are finished. And what I'm concerned about is I'd like to see somebody like Oracle, NVIDIA, some of these people get together and start to make this chip and start to make the data center that would run off of an electro-optical quantum computer. That should be happening. It should be happening at least at the same time that they're hedging their bets, betting on the old system. And to put all your money into big data centers for digital, which I think everybody knows right now is hackable. Yeah. and with quantum computers, and I'm sure some people out there got them, they can hack any of that stuff. So anything that really needs to be confidential, that needs to have security, it doesn't exist anymore, or it won't shortly. And so to bet on things that are hackable and require huge amounts of energy, and they're going to be a million times slower than the kinds of things that I've suggested, that's a mistake. I mean, some of you probably play video games, and what happens if you got the slower computer?
Yeah,
you get killed. You get killed. And if you take that to real life, real war games, what happens with the guy with the slower computer and the slower missile and the slower defense time? I mean, the slower plane, the whatever it is.
Yeah,
you're going to lose.
Let's get back on track. Andre had a question. Go ahead, Andre.
Yeah, thank you. I think you started the discussion with a discussion about the transistor and its ubiquity in computing, but there's not really an optical analog of that nonlinearity of the optical transistor, or at least not a good one. And so it kind of limits the kind of computations you can, because optics are good at linear transformations, but to do what the fundamental the transistor does, which is nonlinear, is harder. So how do you foresee these optical computing schemes overcoming that difficulty?
I think some of that has already been done. And I would encourage you to go to the website for Qant, q.ant. They're over in Germany, and look at their processor. Look at what they're doing. And I would also look at Xanadu. And
there's not much information on their website.
Look, I've looked at their patents. I cite them in my last patent. You can look at their patents and really get into the weeds there. They get a lot of them. And look at light matter and light intelligence and Mythic and a little bit AR Labs. Those are some of the folks out there who've been generating intellectual property, and they've got patents, and the patents get into the kind of detail you want to look at. And if you want to find a whole bunch of them real easy, you can go to my LinkedIn page. And in the first 10 attachments, I have a couple things I've written about what we're talking about today, like a summary of my patents. And then I talk about AI and quantum computing and say pretty much the same things you've heard today. And I've got attached several of my patents. And I included the last one that's pending right now, which I didn't have to do, but because, you can wait a year and have to see it, but I put it up there. So the specifications there, some drawings are there. And in the specification, you'll find he mentioned half a dozen companies I've mentioned. And then you'll see big paragraphs listing all their patents. Okay. Which I have incorporated by reference into my patent, okay, if you know what that is in patent speak. So, I took what I could find, the best that I could find at the time that I filed it. And, I'm very transparent with the patent office. Here are the companies that I'm aware of doing stuff in this general field, and here are their patents, have at it. So, it would make some very quick R&D for you. You can just go look at all the work I did. I guess it's free because I put it on public forum, right? You can look at it. I mean, it's proprietary because I'll get claims out of it, but you could get caught up to speed pretty quickly. There's been some things that have come out in the last year since I filed it. It's been a little over a year, and I'm watching those things, and some of those things that'll go into the next patent I file because, there'll be a different date. And here's what's happened since the last time I downloaded all this information. But I'm tracking it and looking at what people are doing and making mental notes that, oh, these guys got that. That would work great. That gives this piece and this gives this piece. And boy, we could put this together. So what I'm looking for out of it is I've figured this out. I've been granted some pretty valuable pieces of intellectual property that some company, somebody out there should want to have and own, because I think everybody's going to be needing this and doing it. And it could be cross-licensed to a lot of people in the industry, kind of like the patents for RSA encoding, cryptography was licensed to a lot of people. So I've got this stuff, and I think what I'd like to see is somebody say, gee, Rob, we get it. We'd like to have those patents or own them or license them, or maybe we would like to do a deal with you where we get them and we can use them and we can license them. We'll have a split on cross licenses to other people, because probably darn near everybody's going to want to do this. And so that's kind of where things are at. And I can't control other people and what they think or do. I can only focus on what I'm doing, and that's about it. So I'm figuring things out, and I'm filing patent claims and doing a little podcast like this, so the word kind of gets out that, hey, there's this Lyden guy, and he's got this stuff kind of figured out, and he kind of knows where things are going. And gee, we should hook up with him and have him consult with us, and then we can make some of these things and have an optical computer, electro-optical computer. We can have a data center that's got a relatively small footprint and doesn't burn a whole lot of energy, and it'll make this other stuff mostly obsolete, and that's okay. That's progress, So I gave up a long time ago trying to predict what people and companies will do I would think there would be at least one of them out there with enough sense they can read a patent claim at least, and also have technical people who are bright and can see what's in there and realize, gee, that's pretty cool. So we'll see,
Well, and also, I mean, there's other applications. I mean, I see, drug discovery and those kind of things where, this would be huge.
Well, the computing
solution.
power, the computing power part of it, the ability to process so much more information, so much faster without burning a lot of energy. Yeah, and some of the things, like the way I call it the DNA storage of memory, you could use that to create, right now I think with Unicode, there's like, what is it, 1.5 million, coding points or something. And I basically showed, if you do this DNA stuff and you have 4 or you have 8 different, you got trillions of data points. You could individually encode every word in the dictionary, every doggone thing with a single. So you can create a lot of coding points, which gives you the ability to manipulate a lot of data too. But I think the key thing is that light's the fastest thing we've got, and it doesn't burn up much energy to send it or process it. And a lot of smart people have figured out and got pieces of the puzzle already. And it's really, I think at this point, the exciting and the fun thing would be, let's get together with somebody who wants to put them all together and make this optical computer or electro computer. And nobody's made that kind of optical processor, optical memory, optical processor hybrid that kind of acts like the brain and is able to do all this and simultaneously input, output, crosstalk, perform processing things all at the same time, all in parallel, a whole bunch of it. And I believe it's doable. I mean, if I can say it and draw it out in a diagram, how is that not doable? If somebody has to get the idea that, gee, that skips several generations of steps of, it kind of gets us from here and leaps ahead to a different point. And it depends if somebody wants to get to that point today or in our lifetime, I guess. But I think it's doable.
So we've talked about processing, we've talked about, computing and communications.
Sure.
What about encryption? What is the application and how would this work?
Well, I guess the first thing to say is, I think everybody knows that with Shor's algorithm and a quantum computer, you can bust digital codes. And, there's the RSA, there's elliptical, there's other things, there's quantum,
but not looking at busting it, but how can we beef up encryption with this solution?
I think the first thing is you don't use digital. And so what I'm saying to do, this is not digital, this is analog. This is using light. So the first way to get some security is realizing that digital is slow, digital is hackable, and slow and hackable is not a good combination, So you want to move from slow and hackable to fast and not hackable, and that would be moving to analog and moving to using light in the way I've talked about. So right there gives you a pretty good leap out of the fire, and there's some people say that analog is not hackable. And I kind of am of the opinion that, like an old coach used to say, something that's, some things are hard. Impossible things just take a little longer, take time. Hard things take time. Impossible things take a little longer. So if it's impossible to hack analog, it could probably be done at some point. Somebody will figure it out. But I have already anticipated some of that, and I've in the patents that I've got out there and other things up in my head, because some of it I don't know that I should put out there. I've shown some ways that you can make analog very difficult to hack.
Go ahead, Jeremy. I want you to chime in with that question you put in the chat.
There a question coming in?
Well, that was Jeremy.
There would be if I could outsmart mute on my system. Sorry, I came in a little bit late.
That system will get you every time.
I came in a little bit. I'd like to catch me up. What makes analog unhackable? I've read about defenses that make quantum difficult because reading it changes the quantum state. But what makes analog unhackable? What am I missing?
That would be a discussion that would take a lot of time and probably go over everybody's head, and so I won't go into it. If you want to talk to me about it privately, if we have a business relationship, maybe we can talk about that. But I'm not going to go into that too much. But let's just say that analog is, compared to digital, pretty unhackable, especially if you do certain things with it. And some of those things I've talked about in the patents that I've done, and you can go there and you can read it. Okay.
But everybody received the patents were attached to the invite.
Okay. So. Now, where you get to unhackable too with analog is that they're trying to move from the previous encryption methods with digital, and they're trying to get to quantum computing with digital. And with quantum computing with digital, there's quantum cryptography, okay? And what you have to realize is that, yeah, they're doing it, but they're still using digital to do it. Whereas what I would suggest is that you do quantum using the analog. And so you're switching from digital to try to do quantum computing. You can do quantum computing, frankly, with optical easier, and then you're already in a medium that's less hackable. So you can do quantum with an optical computer, and frankly, I think you can do quantum computing with an optical computer even better than you can with a digital.
Yeah, I agree.
I think. Whereas with the digital computer, you're creating this superposition, which is basically a correlation, and then you call that entanglement, and you're sending it digitally. Well, you can create that correlation in analog and send it non-digitally, and still have that correlation. And by the way, you can not only correlate those two, but you can probably do 300 or whatever big number you want to think of that seems like a big number. You can do a whole bunch of those correlations and send them all at once in parallel. So that's like, holy cow, in terms of like encryption, the slow boat of digital, and there's got this correlation, and then we open up the box at the end to see if we got a 1 or a 0. Well, think about sending, 64 of them, and 64 correlations, and it's not going by digital, it's going in a couple femtoseconds, and maybe some of them are fakes, and you wouldn't know even which ones to look at to try to hack them. You're going to try to hack them all, and maybe it's all information and it's all stuff being sent. Well, maybe only certain ones are the ones that you're supposed to really look at and try to. There's a lot of different ways to do it, and usually, as you know, probably if you use elliptical cryptography or RSA, when you start taking numbers and putting small numbers up into the exponent part of numbers, and you start putting random numbers up there, with them, it gets to be pretty darn hard, and as opposed to just trying to figure out, geez, is it a 1 or a 0? Well, try figuring out every frequency and wavelength in the visible and invisible light spectrum, and it could be any one of them, or in between, nanometers, and that's a lot harder than just trying to figure out if something's a 1 or a 0.
Yeah, I want to bring some people in from the chat here.
Sure.
So the first, I think it's Al, just put something in about stream cipher versus block cipher.
Well, that's getting into blockchain stuff.
So did you want can you unmute and talk about that?
Yes, can you hear me?
Yes, we can.
Okay. With respect to encryption and quantum computing, you could use the standard encryptors they have now. On the low end, an encryptor, on the low end, quantum computing is about 1 million times faster. On the high end, it's about 3 billion times faster. So on the low end, you would have to use a 512-bit encryptor. Would have to encrypt the data about 40 times for a 1 million bit for a low-end quantum computer. And you would have to run the data through a 1,200 times for a high-end $3 billion quantum computer. So that basically destroys all the data communications, because you're talking about 40 encryption cycles going through on the transmitting end and 40 encryption cycles going through the other side. So what happens is the data transfer rate is 1/80th of what it would be now for a 1 million bit encryptor to beat quantum, and it would be 2,400 encryption cycles to go through to beat a high-end 3 billion bit, a quantum computer run 3 billion times faster. How are you going to defeat that?
Well, one thing, I'm not using the digital system.
Right.
And that's key. I once sat down, and I don't have it in front of me, so I can't throw out the numbers for you. But, if you look at what happens in a neural network, and where usually in a neural network, for example, there's an addition and there's a multiplication. And anytime you start adding computations in the situation, the difference between using directly encoded light and the digital system starts to really snowball. The more computations you have to do, the bigger the numbers you have to try to crunch, the relative slowness of digital, a picosecond for a 1, a picosecond for a 0, as opposed to maybe as low as a femtosecond, maybe it's 20 femtoseconds or 30 femtoseconds, let's say. That difference in speed every time you try to communicate a number, and when you try to process a number, the difference in speed when you start having to process a lot of numbers, big numbers, and that happens when you get into what you're talking about. It becomes slow and energy efficient to do it digitally. Whereas with analog, you're just so much faster and it requires so much less energy. And so I think the speed at which you can do those things and the amount of energy you need, the speed's faster and the energy is less. And so that's how you tackle it. You tackle it by not using digital. And so, can that be done? Yeah, I think that can be done pretty easily, actually. I don't know if anybody's doing it. As far as I know, not. But, the kinds of things that you're doing right now with digital to create these blockchains kinds of things, some of it I don't think is necessary. But if you wanted to replicate exactly what you're doing and do it, optically, you could do it. I don't know if that answers your question, but.
So are you using entanglements, you deal with the man in the middle issue. Quantum entanglement, are you going to use that to make sure that somebody in the middle?
I think you can do a couple basic things. I mean, right now, I mean, most of cryptography out there is RSA or elliptical or some hybrid of those things, let's say. So the existing stuff that you have, if you just wanted to replace that without getting into anything fancier, and you just wanted to do it in analog instead of digital, you could do that. And it would be faster, and it would be cheaper, more energy efficient, and it would be more secure. Now, when you make the next leap, there's such a thing as these quantum computers they're making right now. I would qualify the words there and say they are digital quantum computers. There's something we can call a optical or electro-optical quantum computer. And it's a different animal. And it doesn't necessarily use digital. It may have digital stuff processing along with it. It may be a combination of both digital and optical. But it can do quantum computing too. And I think faster, easier, with less energy than can the digital ones that we're playing around with right now, at least that we see in the press, But
now when you're talking about the optical quantum, are you still, you're not talking about entanglement or anything like that.
Well, you could have entanglement with optical. Entanglement is basically a superposition relationship or correlation as its own digital between two things.
Right.
You've got two things, you're creating a correlation between the two. There's a superposition, which is that correlation, and then that correlation you're calling an entanglement, and it stays with it, even through distances and time and so on. So can you create correlations between two things in analog? Oh, absolutely. You can take a light, shine it through a prism, and when it goes through that prism, guess what? Because it's the same light source and they're going through the same optical device, there's a correlation and relationship between each one of those wavelengths and frequencies of light leaving that prism. And, you could do the linear algebra to describe what it is and what those relationships are. And you can know what terahertz each one of those colors are, what nanometers each one of those are. Is there a relationship between them all? Yeah, you bet. They're all flying from the same light through the same prism, and they're heading down the track, so to speak. So is there correlations there? Sure. Can you call some of those or make some of those to be entangled? Yeah, I think they're kind of inherently entangled because if you know what one is, you can know about what the other one is. For example, if you take a sine wave, and
that's an economic question.
And how they do this right now, well, there's a lot of ways that they're doing it. Part of how they're creating the quantum thing right now is they'll send a sine wave, let's say through optical fiber cable, and they're going to send it in call it a vertical orientation. And then they'll send a second one, let's call it a horizontal orientation, a little bit later than the first one. So it's called phase shifting, starts out a little bit later. And so when you're looking at this sine wave, where one is positive one, where it's zero, where it's negative one, right? Because that's just the way a sine wave goes. And if you know when the other one started and you know what frequency it's at any point when you know what one is on this one, you can know where the other one's at too. That's a correlation, and that's called an entanglement. So can you have different frequencies of light that, for example, start from the same light source or go through the same optical device? And is there a correlation between the two of them? Yep. And can you call them entangled? Yeah, I think you could. And you could send a whole bunch of them, not just two, So that's kind of a simple Simon kind of way of trying to get that across. But yes, I think you can have quantum entanglement with different wavelengths and frequencies of light. And you can do it optically, not just digitally. And I think that's where things are going to go, and where they should go, because it's a lot more efficient, and it'll also be a lot less hackable. Because the weak link in what they're doing right now is there's digital in the link, you know?
Yeah. Simple economics question. We literally have trillions of dollars in the current equipment that we're using for data communications. Yeah. Okay. So what we need is a migration path. Economic. They're not just going to throw out trillions of dollars of communication equipment without a viable economic path to upgrade to the new technology. How do you see that?
Well, actually,
let me answer that. Let me answer that real quick. I mean, but before you get in, well, I don't want to answer it. I mean, I just want to address it.
Sure.
So that, the next two sections that we had set up for this call were to first talk about what's the current state of the art, and then the next was what's the art of the possible. And as part of that, that's something that we need to do. And I hope to set up a consortium with Robert and the people on this call that want to be part of that to start moving this forward. I mean, we've already started in the chat to identify companies. We know that there's a huge power savings, and so we need to look at bringing all of that information together as a group and start finding what is the current state of the art and how do we do that, and is there a path where we can transition from digital to optical with steps where we're integrating optical into our existing digital.
I mean, I think the good news is that the train tracks have already been laid, in a sense that we have optical communication systems all across the country and the world. And right now, they're usually just sending a couple frequencies, and they're sending ones and zeros. But there's nothing saying that those train tracks can't carry a different train, and they can carry multiple optical signals, not just multiples that are only ones and zeros. They can do it right now, and they can certainly do it with some of these things, optical devices like wave division multiplexers. So I think the train tracks are there. That's the good news. We just got to put some different trains on the tracks, and more than one, and trains that have a bunch of different colors on them. And so would some equipment need to be renewed or switched out or whatever? Yeah, probably in some places, but the basic stuff is there. The optical fiber is there, and they're always making better optical fiber. But the train tracks are there is the good news. And I think the good news is that a lot of the parts for these optical computers or electrical optical computer hybrids, they're there. You can start shopping right now and start putting one together. So I think a lot of the parts are there. And like I said, I think the biggest missing piece, I think most of it can be put together right now. The biggest missing piece in my mind is getting that better optical memory, optical processor hybrid, putting the brain together. To me, that would be the key piece to do. I mean, right now, could you do it with a single holographic memory? Yeah, you sure could. You could store it. It'd be quick. It'd be quicker than what we're doing now. But you're going to want to make it more like the brain, where it's processing a bunch of different inputs simultaneously and cross-talking and performing logic functions. And, why not do that? That's just a matter of wanting to do it, I think, really. And and then the challenge then becomes, well, you can do it, and you can do it on a tabletop. I think that could be done on a tabletop actually fairly quickly if somebody was motivated. And then the question is, okay, now we got it, it works. How do we make it small? How do we make it small enough to fit in my my iPhone or that kind of thing? And that becomes the next challenge is making it smaller. But whether you can do it and have it be in like a data center or something, oh, sure, you could make one and have it on your kitchen table, I'm sure. So
we got to start somewhere, and that's
you got to start somewhere. So start big and make it work. See that it works. Well, that's great. Now we got to make it small and make it even more efficient and so on. But compared right now, I think it would be a lot smaller than these huge data centers, and probably if it's 1 million times faster. I mean, wow. I mean that's a lot of bang for the buck on your kitchen table, So you got to start somewhere. I think you start with making it and having the proof of concept. And I think there's a couple of people out there I see trying to make optical computers, electro-optical computers right now. And I don't know what their memory storage mechanism is, if they're doing it on a disk or a tape or film or however they're doing it. But you can do it on flash. But I think you want to have a hybrid holographic optical memory and processor device where they're right together and kind of in the. I thought the geometry to start with that might be good would be to take the 8-sided octagons, because then you'd be able to take digital data, and turn the digital sequence into a parallel thing. You could actually process digital in parallel that way. So it would help us kind of get from the old system and talk to the new system from the new one, where you could actually, it's digital, but we can turn the digital into optical patterns, or by the way we set up our processor, we can take it and we can actually process the digital in parallel. That would help, talking back and forth,
Just and for aesthetics here, when you moved your computer, the reflection off of your camera it's covering your face.
Oh, okay. Well, okay. Better. I'm over here and dodging the. Sorry.
Yeah. No. It was all right.
Not that you need to see me. I think probably hearing me is probably more important than seeing me with my old cap that I have on. But anyway, so I think it's doable. The question is, okay, I figured out this much, and it's like making a movie. Maybe I'm the screenwriter here, but it takes a hell of a lot more than a good story and a good script to make a movie. You need a producer, you need a director, you need grips, you need all these people who've got talent. You need people to write software. It's a big job. So the question is, who would like my script and like my help in terms of know-how, helping you make this movie? And the question is, do we got any movie makers out there who want to make this film?
And I just put it in the chat because someone had asked about wanting to keep this conversation going. Is that in a description of what we're going to talk about, I wanted to set up a optical computing consortia with anyone here that wants to be a part of that. Just please drop your email in the chat, and then we can bring everybody together. We can do it every month or every 2 weeks, whatever everybody decides. But and then we can do that. We can start finding the producers, and we can start finding the funders, and we can start finding all the people that we need to take your script and turn it into a production.
Well, and the funny thing, long and short of it is, some of the people advising the president, I mean, Larry Ellison is a very bright guy. And I guess Alon doesn't do that anymore, but Alon's a very bright guy too. And Jensen Huang at NVIDIA, I don't know how he keeps all the things that he's doing straight in his head without going completely insane, but he's a very able man. And I watched his talk the other day on Monday, and, you know, these are impressive guys. And frankly, they should know about this, especially if they're advising the president. And if we're spending billions of dollars on white elephants, that's going to be a national disaster. Because if somebody else does this, and you know, my patents are public. You know, somebody in China sees this and they do it first. What are the implications of that? If a bad actor, just, you know, some gang member somewhere who's got lots of cocaine money or something wants to do this, what's stopping them? I mean, basically, they hire the right people and take the roadmap and do it. And you know, there's a really good example of this. You know, one of my fears is that, geez, am I going to be like Sir Basil Henry Liddell Hart of England, who after World War I wrote these books on strategy, the indirect approach, and he'd been involved with tanks, you know, introduction of tanks in World War I. And of course, the British didn't listen to him, but General Guderian did in Germany. And that's what happened in France in 1940. He took the indirect approach. Instead of attacking the Maginot Line, he went around the Maginot Line, and France fell in about a month, you know. So, you know, it can happen that you can write a pretty good screenplay. You can't control sometimes who makes the movie. And, you know, if somebody in the United States doesn't get with making the movie and somebody in China or somewhere else does, we're screwed. And could be for a long time. You know, I have patents, and that gives me the right to make, use, and sell it in the United States, but I can't stop what people in China might want to do, or somebody somewhere else. And the funny thing is, you know, Brian and I were talking about this last night. Well, geez, Rob, you know, who do you think would do it faster? You know, the U.S. government or a bad actor or this or that? And I said, well, the Chinese would do it faster because they'll look at the patent and say, this guy, he's in America. He's not our friend. He's the enemy, and we're going to knock him off. Whereas somebody in America who's got an ego, who's got a big company, I won't name companies, but there's a whole bunch of big companies doing computers. They're going to go, well, who is this guy? He doesn't work for us in my department for me. And they're going to want to tend to deny it at first. I've been through this before. They kind of deny what you're doing. and then they go through the stage where they deny it. And then they start realizing, well, shit, the guy's right. And then it's like, well, we got to get working on it. Then they start working on it. And then they start doing it, and they start knocking you off. And then finally you find out that they knocked you off, and then you got to sue them. And then you're the enemy who did this terrible thing to them, you know, because you thought of it first and they knocked you off. And that process happens, and I've been through it several times. I won't mention the companies. That takes a lot of time. And you know what? The Chinese aren't going to take that kind of time. They're not going to have the ego problem. And neither will a bad actor. A bad actor isn't going to go, geez, I got this company and all this and that. And gee, I don't know if I want to pay this guy or that, because they're not going to pay me. They're just going to go do it. The bad guys are going to go do it. Different countries can just go do it. They don't have all these hem-haw, you know, things to do. And frankly, if our government right now decided it wanted to do it, typically the red tape and all the meetings they want to have, and, you know, administrative bureaucracy can slow things down a lot. And this is something that would mean if a bad actor or a foreign country wanted to do this compared to us doing it, they'd probably both get it done faster than we would. And so in my view, this computer stuff it's serious stuff, in that the guy with the fastest computer is going to win. And I really wish we could do kind of a Manhattan Project kind of thing with this, where we kind of cut some of the red tape and all the meeting bureaucratic nonsense that goes on. And look, we need to get this done. We need to get it done as fast as we can possibly do it, because if we can do it and think to do it, somebody else can too. And who's going to get it first? And the result of not getting it and being able to control that part of it is potentially catastrophic. So I don't know. I don't have control over those kinds of things. I don't know if there's some part of the government that actually can move quickly to do things. But to me, it's like government should be partnering with, and they have, Oracle or Ellison has done things for certain agencies of government. But somebody should be saying, Larry or Jensen or whoever, this Lyden guy has this thing, and we think it's doable and serious, and we think we want a little Manhattan project on this here. So can we all kind of get together and do some kind of thing and get them in the fold and get the show on the road? Because, if we don't do it, somebody else is probably doing it right now, and I can't control that. And our government may not be able to control that either if they're not here in the United States. So anyway,
yeah, I'll do my part here, because that's a lot of good points there, and I think that needs to be brought up, and I do work with a lot of federal agencies, and I can get this to Joint Chiefs, which I think is the place that we would need to start. I prefer the top-down approach to the bottom-up, and
yeah, I think if they could speak to, there's several people on President's panel on all this stuff, and one of them's Larry, and I don't know if Alon is still there too, but Jensen, I think, is a pretty impressive guy. I can't pick him. It's not my job to do that. But if I had my dream meeting, it would be having Larry and Jensen in the same room, maybe with Alon there too, just to create a little excitement, and with some people from some government, say military, and some agencies, and maybe people like somebody from Raytheon, somebody from Lockheed. And those are the kind of people you'd want to have in a room,
Yeah, you're going to have them all in the room, because, Raytheon, Lockheed, they're not going to jump without knowing that there's funding to support it. So right. That's why if you're going to do it through the federal government, you're going to want to start with somebody, maybe even NSA or.
Well, I didn't want to use that word, but yeah, they should be. It'd be pretty close to the top of the list of people who should want to have this, and they want to have it first.
Exactly, and they're all part of this community. They're all part of this ecosystem.
Right. I think they would be the ones to want to have it first and have it really figured out and perfected before it gets handed off to the kids. Because you start handing it off to industry. There's some people there that are fairly teenage-like in their outlooks on things, and their motivations can be just make a lot of money, and they don't care about how they do it and who they sell it to. And so I think it would make sense for national security people in general to be on top of this, and to get it done right internally, and then decide how to roll it out and who to roll it out to and who to license it to. But I think NVIDIA would be pretty on top of that list, and probably Microsoft isn't too far behind. And there's IBM. There's the usual suspects to go out and round up.
Right. But that's not always the best place to start.
No.
So
I think you want to start.
We have to find where the pain is, and that's the key. So that's why I say we start with the Joint Chiefs.
Where the pain could be is in a national security area. So like Joint Chiefs of Staff, certain 3-letter agencies, they should, and anybody dealing with cryptography, they should all be like shit, we better, excuse me, we better get this, figure it out, and have it down, and then we decide how fast to disseminate what portions of this information to industry so that everybody can have more efficient computers, and we save a whole lot of money. We save a whole lot. I mean, that's a national security issue right there. Just the amount of money and the amount of energy that right now is going to have to be used to try to do things the way they're trying to do it now. There's a pain point, and this can eliminate that pain point or substantially reduce it, probably by 60% at least. And that would be a good thing to try to do, and to try to do fairly quickly. But the security issue is like immediate. That's not like, someday it'd be nice to have a better laptop on my desk. That's more like we better have that laptop on our desk and make sure nobody else has it, or if they do have it, at least we've got one as good,
Right. Yeah. No, and when you're talking about power, I mean, and the data centers, I mean, Alexander put in a really good comment in the chat where he was talking about, light being able to travel long distances without degradation. And, data centers wouldn't be centralized hubs. They could be a satellite collective of access to cheaper energy.
Yeah. And what you'd want to do, from a practical standpoint, a commercial standpoint, but also a national security standpoint, you want to just have one hub. You want to have a bunch of them redundant so that the system won't fail, can't fail. Let's say there's a national disaster of some kind, big earthquake in California, and half of it slides off in the ocean, or Silicon Valley goes in the ocean. Well, you want to have what's in Silicon Valley a couple other places, so you don't lose it all.
Oh, exactly.
Taiwan gets whatever. So I think with the kind of computer we're talking about, you want to have a distributed system, not a totally centralized one. I mean, certain things you want off the grid, the national security stuff, but you want some redundancy. You want it to be able to survive issues and problems, and that's doable. And it's easier to do if you don't have to build such big data centers that are so damn conspicuous and take so much energy and are such nice big targets. If you have the power in your laptop right here to do what a supercomputer does right now, wow, that's pretty cool. And I think actually an optical computer or electrical, there'll always be electrical involved, an electro-optical computer that's also capable of quantum stuff you'll eventually get it in a laptop or a phone size device.
Yeah.
And wow, think about that. Having these big data centers or these big supercomputers, and it's on your phone. Wow. But it'll get there, but it won't get there with digital. That's for sure.
I see people are unmuting. Alexander, I see you're unmuting. Is there something you wanted to say?
Oh, just to add to his last point, I think it's really three different types of products. You do have the data center side stuff, anything from a computer to a supercomputer, but you also have these a niche market like the Raspberry Pi, which would almost be a really cool place to start, because they're small computers that would be able to have a lot more functionality. But it's also kind of cool to think about how, many different types of applications they have, including, quantum elements of encryption for military applications. You have small computers on board.
Yeah, and that's a good point too, because one of the presentations that's going to be coming up in May, I believe, end of April, early May, is about custom FPGAs, and that is exactly what Raspberry Pi is. It's just a FPGA.
And you were pointing out that you can run a train on this kind of railroad or that kind of railroad. I think that's a really good analogy. But while you are running some traditional computing on like the photonic rails, I guess, you still kind of want to build them from the ground up, because to represent something in binary on these new rails is not really using them as deeply as they're meant to be used. So you kind of need to like rebuild some of the operating systems at some point to use to more efficient use case. Is that wrong or?
Yeah, you will. I don't know how often optical fiber and all the interconnects and the amplifiers and such are being renewed right now. Wouldn't take a lot to figure that out. You could call some of the phone companies and they probably, tell you, call Verizon, maybe they can explain not only your phone bill, but, tell you about some of this stuff. So, I mean, this stuff is always being upgraded. And I think something like this coming along would kind of push for an upgrade in the kind of cables that are being used, and the kind of wireless kind of communications that are being used. And I think that's another whole big area to look at. So yeah, it would push for better train tracks, but there's enough there to start right now, and I think once again, depending on what you do, you can build it on your kitchen table size, and if you want to get specialized optical fiber cables and special interconnects and the latest and greatest stuff, state-of-the-art stuff, you can do that and you can get it all figured out. And then when you want to commercialize it and roll it out and who's going to have it and who should have it, then you can make decisions about, okay, do we lay some new tracks here or there? Do we provide this sort of equipment here or there to do that? And, those are all decisions you can make. But first you got to do it, figure it out, and know what the best thing is, have the best things figured out so you know here's the optimal target here. This is what's possible. And if we want to make this available, what's the cost benefit analysis on doing this thing or that thing or the other thing, and timelines as to, okay, when are those things being renewed anyway? And you make sensible decisions about when you roll out what and what parts you replace and when. And because the whole world doesn't necessarily need to have, optical or electro-optical computers tomorrow. There are quantum computers. Not everybody needs a quantum computer on their desk. It'd be nice to have, but not everybody needs them. But certainly some people do need them, and people in government definitely need it, and defense definitely need it, and they need to have it first. And then if it comes along, it's great. But for most of the things I do, I've got this laptop here. I think I bought it in 2017. It's considered ancient, but it was a pretty good one. It was supposed to be like a gaming one. It has great memory and everything. And for me writing my patents and screenplays and doing a chat like this, it's really all I need. I really don't need the other stuff. Now, would it be nice to have it? And sure. But not everybody needs it. Not everybody needs it now. It would be good for everybody to get to the point where they could, because everything would be more efficient and we'd all be using less energy. But, the people that need it now are the government agencies you talked about, and the military and national security stuff. They're the ones that need it and need it right away, like yesterday. And the rest of us doing normal stuff. Sending emails.
Yep.
We're not that important.
We got about 5-10 minutes left.
Sure.
I do want to. So Steve, you had your camera on the whole time, and I've been quite impressed at how diligently you've been following everything. Would you care to comment, or is Steve Sokoloff?
I mean, I think it's been an interesting conversation. Look, I'm a venture capitalist now, and I'm started out at Lucent. So I've come from the telecom and networking space, and photonic computing and photonic memory have been, sort of dreams for a long time. And I appreciate the discussion. And, I think it's, the challenge of making it and showing that it can be made.
Cool.
All right, thank you. So before we wrap this up, I think we've covered a lot of information, had a lot of good interactions here. There's a lot of stuff in the chat I need to share with Robert and everybody. But yeah, like I said, please, I don't necessarily have everybody's full names here, and I don't have your emails. I do that on purpose because I want people to feel comfortable if they want to be anonymous in these forums. I don't want to pin anybody down if they don't want to be pinned down to what it is that they do. So if you would like to be part of a continued process of moving this forward, moving this technology forward with a consortium, please put your emails in the chat, and I will reach out to everybody. Otherwise, I will be going through everybody that was here and try and track down your emails in the 13,000 plus people that are part of this community. So that was all I had. Did you have anything, Robert, to wrap up?
No, I think I talked too much already.
All right.
I wish there'd been some other questions, but it's okay if people got something out of it. That's great. Hope somebody did.
Yeah, I mean, and there's going to be, this will end up on YouTube, and there'll be more interaction because of that. I am going to strip out all the stuff about China and bad actors, because I don't want to give anybody those ideas when this goes on the YouTube
you might as
channel.
well not telegraph it, I guess.
Yeah, exactly.
Why advertise for it?
Exactly.
But
that'll all be edited out.
Yeah.
No, we know that, and we deal with that with other technologies that are,
right,
that are really beyond. And I feel your pain, because back in when I started this originally with the federal government, and we were focused on, solutions for the federal government, as I was a civilian employee then, we found this company that was able to transmit on the radio frequencies on any difference in medium. So on the surface of the water, they could transmit from inside of a skiff to outside of the skiff by coupling to the metal in the walls and through the door hinges and stuff like that. And when they first presented on the forum, the biggest challenge they had was everybody was questioning the physics and saying that what you're saying defies physics. And now they're coupling. And so now it's been accepted, and they're doing underwater communications by coupling to differences in temperature. And it's just
listening
amazing.
To propellers and things like
exactly.
that. Yeah.
all the stuff that they're able to do with that technology now is just incredible. And so we got to get past that.
Well, I was kind of pleasantly surprised that nobody tried to say, Rob, you're an idiot. None of this is possible. But I think what's happened.
I was surprised too. I thought somebody was going to come out there and say
usually you get at least one who, but I think what's happened over the last year with this daily bombardment of photonic this, optical that, everybody in the computer industry has suddenly gone photonic optical crazy. And it's really only happened in the last year or less,
Yeah. No, you're right. And like
but
I said,
it's here,
and we were talking about it at the beginning of this. It's just how much it's showing up in the news. I mean, I just saw something where somebody had an optical processing chip that they were, an article on that. And you've been sending me dozens of articles since in the last 2 months.
Yeah, because I track it, I figure I should. That's kind of what I'm doing. So, yeah, and I don't know that I see everything, but I see enough to kind of tell me, holy cow, I got on the wave before the wave got here, and yeah.
Yeah, and I had to get a new editor because my video editor got a job on a production set, on a movie production set.
Uh-huh.
So I finally found a new editor. That's why your videos haven't shown up yet. So I just got those today.
That's okay. That's. I mean, it's good that you're doing it. I guess if they get out there on YouTube, then we'll get a group of people. I'm sure that'll be. Everybody's got an opinion,
Yeah. No. And then I'll work through my channels too. I'll work through the people that I know in the defense industrial base and at NSA and.
Well, let me know. I mean, you've evidently been getting some messages and emails from some people, and I don't know who they are, and I probably don't need to know, especially in a public forum right now. But let me know who's interested in talking about this, because somebody should get this on the road pretty quick. Somebody on our side, that's for sure.
Yeah, and I have to say, people want to stay anonymous.
That's okay.
So a lot of times people are looking for solutions, but they don't want to go directly to you until they have the opportunity to vet it. Right. And so I kind of play the middleman there.
Yeah, that's understandable.
So that's why I'm not a name dropper. It does
no
no good.
It
just upsets the people.
Yeah, well, just let me know if there's something you'd like me to see or respond to, and I'll be happy to do it. Yeah.
Absolutely.
Okay, are we a wrap?
We are a wrap. Unless anybody has any questions.
I have one question.
Yeah, go ahead.
Based on what you described here, what I see is a need for a photonic FPGA, which I don't know if they exist yet, to be able to handle filtering all the various light wave frequencies you're talking about, to handle the endpoint of the optical communication devices.
I can tell you that there are devices that are capable of sending multiple wavelengths accurately and also detecting the same. So I can tell you that kind of equipment is actually already out there.
Okay. Thank you.
And I could tell somebody if where to go shopping for it. If somebody comes back and is serious about doing something.
Okay.
Okay.
All right. Okay. Thank you.
All right. Thanks.
And a lot of good information there. And I'll be sending you access to the video and the transcripts.
Sure.
Robert.
I'm sure if I show it to my son, he'll have fun with that. Dad, you big goof,
Yeah.
Well, he's at the age where he's actually starting to realize that actually Dad does know a few things about life. I think he's past the stage where Dad doesn't know anything about anything, and so he's starting to Starting to get over
Yeah, no,
it.
my son. I mean, well, he's an adult now, but he's he's like, I thought you were an electrical engineer, and you're talking about all these different things on your forums and.
Yeah. Well, I started out with a master's degree in history and public administration, and then I was a coach. I was a teacher and a coach, and I coached a couple of people, made Olympic teams, and then I started inventing things a lot in the sporting goods industry. But so this computer stuff, it's been a growth stretch, for me to get into this in the way I have, and you can't say why it is this sort of insight or intuition comes to you. You can only say, I'm not sure if you got the right guy here. I don't have the degree in electrical engineering like my brother, but I'll do what I can. And so I've done the best I could, and there it is. I've written a screenplay, and could the screenplay be improved? Could it have some rewrites? Will it take a bunch of people to make the movie? Yeah, damn right it will. I certainly can't do that alone, and frankly wouldn't want to. So we just need to find, the production company, which is kind of funny, Larry Ellison, they do own Skydance, and now they bought Paramount, and now Paramount's buying Warner Brothers. So it's really funny. They understand things about scripts and making movies too, besides doing software for, I think Larry started out doing software for CIA, I mean, I think that's pretty well known. And,
Yeah, no, and it is, and you talk about your background, and I think I said it in the last forum that there was a company that I'm talking to about using them to be for the platform where we're going to move all these collaborations to, and they do challenges. They don't work from the solution side, and that's where we found our ability to collaborate without stepping on each other's toes. But in their website, they state that it was like 80% of the solutions that come from their challenges that they present are from people the company never would have considered to hire to solve that problem, and 70 some odd percent of them come from industries outside the industry that was looking for the solution. So it's and that's the challenge with the silos, and that's the next big step, is start breaking down these damn silos.
I had an interesting conversation. I'm not going to say who it was, but it was a professor at a major university back east who's been involved in the computer field. And when I talked to him about what I'd done, and I said my background, and I said, maybe it was better that I didn't have a background with all this computer science, this and that, because I would have been so, I don't know, I would have been so much in the box, I wouldn't have been able to think outside of the box.
Exactly.
And I understand. Because I was a complete fool and didn't know all this stuff, I could just start from this position and,
Yeah. There's actually a name for that.
Yeah, I forget what it is.
And it is something naivety.
Yeah, well, whatever it was, I had.
But it's basically that you don't understand enough
to understand
about something.
It's not possible.
Yeah, exactly. You don't understand enough about something to have that problem.
Yeah, I mean, I remember having conversations kind of related to this about creativity with my son, and it had to do because we've written songs and produced a bunch of songs, and whether they're good or not, I don't know. But I tried to tell him, when inspiration comes to you, like for a song or whatever it is, it's usually usually don't get the whole download, the whole song. You get a little fragment, you get a little piece of music or rhythm, or you get a few lyrics. and then you kind of get a few more, and then you start to assemble it, and you don't even know what it is in the beginning you're working on, and you can go online on YouTube and find Paul McCartney saying the same thing, and how that works. It's rare. It can happen that you get the whole thing, but usually it's bits and pieces, and you work on it with your conscious mind, and then your unconscious mind goes to work on it when you're not working on it, and stuff starts popping out. So you don't know really what you got or what you're doing in the beginning, but it's an act of faith or an act of curiosity, and you end up in a place where you never thought you'd be,
Yeah, and I think they call it.
Can I interrupt you guys?
Yeah, go ahead.
I got to jump off.
Sure.
And I didn't want to say this in the presentation, but I thought that, Eugene, we might propose a wargaming simulation whereby a computer system that produces far less electromagnetic radiation, where you might propose, hey, what's the difference between a digital and an optical in a stealth environment? And that I think is quite an interesting thing to try and solve.
I know that the Soviets supposedly kept a lot of analog vacuum tubes and such in some of their equipment because their doctrine was to use tactical nukes, like in Europe, if it ever happened, and so that their equipment would be less vulnerable to electromagnetic pulses and radiation and things that happen. So whether analog in general is less vulnerable to that than digital, I would suspect it would be, but that's getting into stuff and equipment that I think first we got to get the tabletop thing working first, and then figure out the rest of that. I don't know.
I was kind of curious what, like something like the concept of a volcanic basalt and aerogel command tent with a photonics processing system. Is that 10 times less detectable than what we're using now? And then if that is, well, how does that war game out for a war in the Arctic where everything is thermally detectable?
What I can say, what I realize and know is that optical doesn't take much energy, and there's not so much. It doesn't leave so much of an electromagnetic signature of any kind. You know what I mean? You're not sending electrons through wires, and so my guess would be it would be a lot more stealthy, harder to detect because you don't have electrons, strong electromagnetic fields so much as you do with other devices, So I don't know. I mean, in the abstract, could you build a radar system and do some other things that would be far less detectable? That it would be a lot harder to go after.
That's what's winning the Ukrainian war right now.
Mm-hmm.
Is whoever cannot be destroyed. It isn't necessarily who has the better weapons. It's who cannot get tracked down and killed.
Yeah,
by these insane robotic flying
too. Who can make the most stuff, the fastest, like we did in World War II, where we're cranking out how many airplanes a day, and the Germans couldn't do it. So
all right, guys, I gotta go.
I don't know. That's getting into other things, but I'm gonna go. I have to go work on patent claims, and maybe I got to shovel snow again. I don't know. It's been pretty crazy here. Anyway, but thanks for coming, and we'll talk later, huh?